In the previous two videos, we looked at a lot of details about the Diels-Alder reactions, so I thought it'd be helpful to look at some specific examples in this video. Alright, in both of these cases, we want to predict the products and draw the mechanism of the following reaction. Now, these reactions are pretty similar. The only difference is, in the first case, our dienophile is cis. In the second case, our dienophile is trans. So the mechanism for these Diels-Alder reactions is all pretty similar. Right, we have this concerted movement of 3 electron groups. So I think it's helpful to put in dashes on where the new bonds are going to be, so that makes it a little bit easier to drawing in our arrows. And so then, to finish off the mechanism, we're just going to move the electron groups, and we can either go clockwise or counterclockwise. It doesn't matter, right? But they're all just going to move over one space. So these electrons are going to move here, here, and here. Or I could go the other way, here, here, and here. All right, so we know that these are concerted one-step mechanisms, so the mechanism is pretty easy. And so now we just need to draw the products. And if our dienophile is cis, then these 2 electron withdrawing groups have to be in the same direction in the products. So when I draw the product, we'll get our new 6-membered ring. The double bond ends up here, and then these 2 aldehydes, I'll draw them both up. Now, we didn't talk a lot about the stereochemistry in the previous videos, but I'm going to focus on that more in this one. Both of these carbons are now chiral. And so we need to worry about, are we going to get enantiomers or not? Well, in this case, because we have this reflection plane, this compound is meso, and so even though it has 2 chiral centers, it's not going to be chiral, and so I don't have to worry about creating its enantiomer or anything. Okay, so let's look at the same type of thing, only now our dienophile was trans. Now, we don't need to draw the mechanism again. It's basically going to be the same thing as the last one. The difference is when we draw our product now, because our alkene was trans, our cyclic hexene must also be trans. And now in this case, we no longer have this reflection plane. And so there's no reason why, this one would have ended up and this one ended up down, right? They've got to be opposite, but this one could have very easily have been down and this one have been up. And so because we don't have the reflection plane, and if we swap both configurations, that other compound we would get would be the enantiomer. And so we're going to get both this compound and its enantiomer. Okay, we have a similar reaction. In this case, we have an alkyne instead of an alkene, but the mechanism that they want us to draw is also basically going to be the same. So I'll go ahead and draw in my dashed lines for the new bonds that we're going to make. Right, and then I'll just go clockwise again. And now the difference, our product this time, we're still going to make a cyclohexene. Of course, we make that double bond, but then we lost one of the pi bonds from the triple bond, but we still have the second pi bond that didn't go away. So that's going to be here. My carboxylic acid is coming off here. Now I don't have to worry about, am I going to make enantiomers or is it chiral in this case, because I don't have any chiral carbons, right? This carbon is now sp2 hybridized, so I don't have to worry about it being chiral, and so this is the only product. All right, so in this example, we have the cyclic diene. And so this adds a couple additional things we need to think about. We need to think about the endo and exo positions and the fact that the endo position is going to be preferred. We also have to draw the bicyclic system, which can be a little bit complicated. And then also we want to be careful, right? When we draw the bridge, there's not a carbon here, but this is in fact an oxygen. So let's just draw the bicyclic skeleton to start with. So we want to have a 6-membered ring, and then we're going to have the bridge on the top. So to draw that 6-membered ring, as you start by drawing these 3 carbons in the front, and then I'm going to draw the 3 carbons in the back, but it's going to be offset to the right a little bit. And then all you need to do is connect these 2 carbons and these 2 carbons. All right, finally I want to add the bridge with an oxygen at the top. And so there I have my bicyclic system. So, right, we know the double bonds are going to move, right, we're going to form the new single bond, and then the double bond is going to be in the back. So that's always going to be my double bond. And so then the last thing I need to do is I need to figure out in which direction these bicyclic groups are going to be. Now they're both cis, or the dienophile is cis, so the 2 electron withdrawing groups have to be in the same direction. And then we know that they're going to prefer the endo position, so they should both be down. And then technically there's a hydrogen here going up, but for clarity's sake, I think I'm going to leave that hydrogen off. And then we want to think about the stereochemistry. But again, we have a reflection plane going right through the center of the molecule. And so this compound is meso, so it's not chiral, so we don't have to worry about the fact about producing any enantiomers. Okay, so here's another case where we have a cyclic dienophile. So again, I need to draw this bicyclic product, and so I'll do that skeleton first. There's a carbon here now, so I don't have to put an oxygen here. These 2 methyl groups are just kind of hanging out. Right, we have the double bond here, so these carbons are sp2 hybridized. So I don't really need to indicate the directions there, because I don't have to worry about any chirality. Now in this case, my electron withdrawing groups are trans. So they need to be trans in opposite directions in the product. And so one of them's got to be down and the other one's got to be up. So in this case, the endo and exo preference doesn't really matter, because one's going to be endo, the other one's going to be exo. So I'll go ahead and put them in that orientation. But now there's no reason why I couldn't have gotten them in the other directions. Right, there's no reason this one couldn't have been up and this one down. And so I should get both of these products, but you may notice these are mirror images of one another, right? But they're not superimposable, so in fact these 2 compounds are enantiomers. So if you want, you can draw both products, or you could just say, draw the first one, and then we'll also get the enantiomer. Okay, in our last 2 examples, we have a case where both the diene and the dienophile are not symmetric. Right? If either one is symmetric, I don't have to worry about the regiochemistry. But when they're both asymmetric, I do have to worry about the regiochemistry. Right? Where is this electron withdrawing group going to be relative to this group on the diene? And so in order to figure that out, we need to draw the resonance structures. And so we need to see, what the effect of the electron withdrawing group is, and where do I get the partial positive charge on the dienophile. And when I look at the resonance structures, I want to see where do I get the partial negative charge, here or here on the diene. And then the partial positive on the dienophile needs to line up with the partial negative charge on the diene. Now, because we've got enough going on, in these examples in the book, they don't worry about the stereochemistry. And so we're going to do the same thing. We're going to follow the lead there. And we're just going to worry about getting the correct regiochemistry on this one. So I'm going to give myself a little bit more room to draw these resonance structures. So the resonance structures that I can draw for the diene, let me put in my lone pairs. right? And so now I can see I have an allylic lone pair. So that lone pair can come down. That's going to put the lone pair up on the top there. So I'm going to get positive charge on that oxygen, negative charge there. Right? I want to see whether I end up with a negative charge here or here, where I'm going to be connecting to the dienophile, right? And so this doesn't tell me much, but again, I have an allylic lone pair. So I can move the lone pair over. Pi bond becomes a lone pair on the end there. So that's going to lead to this resonance structure. So in my original compound, right, essentially I have a partial negative charge on this end of the diene as a result of the contribution from this resonance contributor. So now we need to do something similar with the dienophile. Right, now in this case, right, what I'm really interested in, I'm going to get rid of that nitrogen. What we really have is carbon triple bonded to a nitrogen. So the resonance pattern I see is I have two atoms with different electronegativities separated by a pi bond. So I can move one of those pi bonds to be a lone pair on the nitrogen. That leaves a nitrogen with a negative charge, the carbon with a positive charge. Now I have an allylic carbocation, so the other pattern I can do, move that double bond over. That ends up giving me a positive charge on the bottom there. And so we can see when I compare, right, the diene is going to have a partial negative on the bottom carbon. The dienophile is going to have a partial positive charge on that bottom carbon. So they're essentially lined up in the orientation that they're already in. So I don't need to flip anything around or anything like that. So now I can just draw my product. The methoxy group ends up on the top, and then the CN stays in the same relative position. And so this is my major product in terms of the regiochemistry. Okay, so this is a similar problem that we had the last time. I have an asymmetric diene, an asymmetric dienophile, and so I need to figure out what the regiochemistry is. And again, because we're worried about the regiochemistry, I said don't worry about the stereochemistry on this one. So I need to draw the resonance structures. For the diene, again, I have an allylic lone pair. In this case, I can get to the resonance structure of interest in just one step. For the dienophile, it's a similar situation. Two atoms with different electronegativity separated by a pi bond. I'll move that pi bond up to become a lone pair on the oxygen. I'm just going to do this in one step, what I did in two steps last time. Right after the first step, I'll have a positive charge here. I'll have an allylic carbocation, allowing you to move the double bond over. I'm just going to do it all in one step. Right, and now we have the situation where the partial negative charge on the diene is on the top, whereas a partial positive charge on the dienophile is on the bottom. I need those to match up, so I need to essentially flip one of them. I usually like to leave the diene alone. I'll flip the dienophile. And so now when I draw the product, of course, first I have a cyclic diene, so I'm going to need to draw a bicyclic structure. just like we've done before. Carbon is on the bridge. We're going to leave the diene alone, so the ethoxy group stays in that position. And then, because I have to flip the dienophile, right, rather than putting the aldehyde here, I need to put the aldehyde here. And I said not to worry about the stereochemistry, but in this case, we know we're going to get the endo preference. So I'll put my aldehyde drawn down. And, almost forgot, I need the double bond.